So first of all, I would like to thank the organizers for inviting me here. It's great to be here again in Moscow. Okay, so my talk is about the, so mainly I will focus on the skein algebra, the Kaufman's bracket skein algebra of the surface. But let me first give an overview of the big picture, which motivates and explains some of the things that I'm going to talk about. So we look at a surface which is sometimes called roller surface with punctures. So this should be, you take a compact oriented two-dimensional manifolds and you remove a finite number of points. So this is a compact oriented two-dimensional surface, maybe with boundary, and you remove a finite number of points. So P here is finite, so that each connected component of the boundary must have at least one. So these are the mark points. So it will not be empty. So, okay, so you have something like this here. Say this is this is the boundary, and must have at least two mark points on this boundary here, and maybe I have one mark point here and another mark point here. Okay, and I will assume that I will exclude a few simple cases where I will assume that the order characteristic is negative, so that you will have hyperbolic structure on this. And there's only a very simple case when you don't have hyperbolic structures. So if you look at hyperbolic structure, say the puncture point should be at infinity, but actually I also allow infinite area, so you will get a picture like this in this case. So these 2 points here, maybe this becomes a real puncture here, and this becomes something like a hole here. So this is the hyperbolic structure on this surface. So these are the points at the infinity. This is the puncture, and this is the hole. So we will look at three quantum objects related to such surface. Okay. So the first one is the skein algebra, Kaufman's bracket skein algebra, which was introduced by Turayev and Prushtishky. Which can be considered as a quantization of the character variety of the surface. So that's a quantization of the character variety. So I will note this by S of sigma. This is quantization of the SL2 character variety. So the second object that we will look at is the so-called quantization of the Teichmuuller space. So this is quantization of the so-called whole Teichmuuller space. Also known as enhanced Teichmuuller space. Okay, so this whole or enhanced Teichmuuller space was introduced by Thurston, and the quantization here of this space was first Rinat Kashayev and also Chekhov and Thang. Slightly different versions of quantization of this enhanced Teichmuuller space. But actually, I will talk about I will talk about the version of Chekhov-Fock, and actually not quite Chekhov-Fock version. It's a refined version studied by. It's called the a square root version of the Chekhov-Fock algebra introduced by Francis Bonahome. And another object is the quantization of the complete decorative Teichmuuller space. So this is quantization of the complete decorative Teichmuuller space. So the decorative Teichmuuller space was introduced by Penner. Well, in the Penner case, he doesn't allow the hole, so he allows the punctures but no hole. Okay? And then Dylan-Thurston and Fuming and Dylan-Thurston, so Sergei Fuming and Dylan-Thurston extend this to the case where you allow also hole. So they call this complete decorative Teichmuuller space. And this quantization of this one here, this is in my work, and I choose this. This is well, based on some work of Mueller. Eventually I found out that what I did is a kind of quantization of this complete decorated Teichmuuller space, which is a positive realization. So this is give a positive realization of the so-called non-normalized quantum cluster algebra. Okay, so this is the Chekhov-Fock algebra, and this is, okay, so let us call this just y of sigma, which depend on some triangulation, and this is, let us call this x of sigma. And the well, each of these two Teichmuuller spaces has a natural boson structure. So the quantization are along these boson structures, and then you can and the big pictures that you have here, so this is the skein algebra of sigma. This is the quantization, so maybe right here, quantization of the, this is the complete decorative Teichmuuller space. And this is the whole Teichmuuller space, this is T whole. And this quantization, of the Chekhov-Fock algebra of the whole here. There's a, so this is F, G, and you have map here, and these are commutative. So this FQ here is the so-called quantum trace map. Constructed by Bonahome and Wong. They call it the quantum trace map because classically this is just the usual map expressing the quantum, the trace of a curve in the Thurston shear coordinate. Okay, so they came up with this, and Chekhov and Fock. So the existence was conjectured by Chekhov and by Fock and Goncharov. So the way Bonahome and Wong came up with this quantum trace map is you look at the classical map and you put power of the Q, quantum parameter, somewhere, and then try to show that it's really an algebra map. Okay, it's a very kind of brute force approach to this, but they show that it really works. So they want to understand, and they pose the question: can you somehow have a conceptual definition of this quantum trace map. And then I show that there is this space and this map G here, so that's GQ here, is actually very simple, and this HQ here. And so both HQ and GQ are very natural, and also the map, this diagram is commutative, and thus gives a simpler explanation of, so from HQ and GQ, which are both natural, you can recover this quantum trace map of Bonahong and Wong. Okay. But in today's talks, I will mostly focus on the structure of this quantum, of this skein algebra of the surface, and another construction of this quantum trace map.
So GQ is an isomorphism or what?
GQ would be just an embedding of this algebra into this algebra. Okay, Poisson non-commutative algebra. It's quantization of the.
So if you know H and G, you can recover F. That's what you said.
Right, yeah. So actually the embedding of this into, and this also embedding of this in here, and the image of the first one is inside the image of the second one. This is the reason why you can recover this. Okay. So this is just an informal introduction to the objects. And now I will begin with rigorous mathematics and definition of, well, this one here and the decomposition of the skein algebra. Okay, so let me now first give the precise definition of the skein algebra.
And what is H?
So this is, you mean this one or this one?
No.
This one here. So this stands for whole Teichmuuller space. Yeah, whole Teichmuuller space. Yeah. So I think that this is the terminology of Fock and Goncharo, and Bonahong used the terminology enhanced Teichmuuller space. Okay, so now so first let me recall the, so what is the Kaufman bracket? So you look at, so D here is a link diagram on the standard plane. So you have any link diagram. Maybe there's another component like this, a link diagram, D, on the plane. Then you can associate a Laurent polynomial, it's called the bracket polynomial, which is in one variable. But I will, for convenience, will extend this to the ring that I denoted by, I will adjoin this square root of this quantum perimeter just for later use. Okay, so R here is the ring of Laurent polynomials in Q to the 1/2. So we associate to every link diagram a Laurent polynomial, D, using the following rules. Very simple. So the first rule is the so-called skein relation. The bracket, so whenever I see a crossing, I can replace this by this Q of this one plus Q inverse of this one. Okay, so I take the overcrossing branch and rotate counterclockwise 90 degrees. So this is the plus. If I resolve these two, I get the plus here. And the other two quadrants give us here the minus. Okay? So that is the rule for resolving a crossing of a link diagram.
Bracket for those two.
Yeah, bracket for these two. Maybe, yeah. So Q here, and I have bracket of this, and then bracket of this one. Okay. So if you do this to every crossing, eventually you get to a sum of, if you have k crossing, you have 2 to the k such diagrams, and now without any crossing. And so each component would be just a circle on the plane, and the value of a circle would be minus q squared minus q minus 2. Okay? So with these two rules, you can calculate the value of any link diagram on the plane. And then Kaufman, well, it's very simple, showed that this is invariant under the circle, rider must move 2, rider must move 3, and so this is invariant under rider must move 2, and rider must move 3 of links on the plane, and under rider must move 1, you have this simple, so I will skip the bracket here, so it's just q minus q, sorry, minus q to minus 3, this one. Okay. So essentially, you can easily show that this is an invariant, I mean, although you begin with a link diagram, but this will be an invariant of frame length in R3. Okay, so this is an invariant, so bracket D is actually an invariant of frame length. An invariant of frame length. Okay, and actually this is a version of the Jones polynomial, the frame version of the Jones polynomial. And probably this is probably the best way to define the Jones polynomial. I mean, the simplest way to define the Jones polynomial.
What means frame link?
A frame link is the link equipped with a normal vector field. Normal means that you have a vector field which is not tangent to the knot or to the link at any point. Okay, so just and as usual, we consider everything up to isotropy. Okay, so frame, so it means that we have a vector field at every point here. That's the frame. Normal vector. Normal here is just not tangent to the link or to the knot at that point. Okay, so that is the Kaufman bracket. And now we will consider frame links in oriented tree manifolds. Okay, so the traditional definition is, so now suppose M, so I think, now M is an oriented tree manifold. You can define the skein model of M. You take the R span of all isotopic classes of frame links in M, and you mod out by these two relations here. So I just want here the relation number 1 here and number 2 here. You mod out by these two relations. You get a big space, well, just a model over R, over the ground ring R. Okay? And that is called the Kaufman bracket skein model of the tree manifold, M. So as I mentioned before, this was first introduced by Duraev and independently by Joseph Brustitsky around 89, right? Well, for example, if you, so what does this mean here? You don't need link diagram here. Actually, you just take, if you have 3 links that are identical everywhere except for a small ball in which this is the picture of the first one, this picture of the second one, this is the third one, then you impose the condition on these 3 links in that model. And similarly for this one here. Okay? So you get in general, a big space. So for example, if M here is S3, or maybe R3, okay, then this S of M here is just isomorphic to the ground ring. The ground ring. Okay, every link here, every link M here is actually mapped to just exactly the bracket of it. That would be the isomorphism. Okay, if M is just S3. Okay. So in this sense, this skein model is a generalization of the Kaufman bracket to tree manifold. Okay. So the size or the rank of this skein model over R is more or less the number of brackets, Kaufman bracket polynomial in N. Yes.
So utility is it evident? Which utility of that?
That's not, well, yeah, that's not evident, but it's part of the theorem of Kaufman. But that's not different.
But do you evaluate Q somewhere?
No, Q is just a formal perimeter. So the ground ring here is just this one.
Yeah.
Okay. You don't need.
Why do you write R but not R or R?
Just R. My R is just the ring of Laurent polynomial in Q to the 1/2. That's it. Okay. That's my R. I mean, not the real numbers here. This R here. The ring, this ring here. Okay. So there are reasons why we would like to study this skein model, and my motivation came from the so-called the age conjecture, but I don't have time to explain that. I mean, there's some relation between the Jones polynomial and the fundamental group of knots. Okay. So this is a model, and there are two instances when we can make this model into an algebra. Okay. So the first is when you put Q equal to plus or minus 1. When Q is equal to plus or minus 1, so say if Q is equal to Q is equal to minus 1, then the scale relation now just say that this one here would be equal to minus. Now you don't need to keep track of which one is positive, one is negative, because it's going to be just like this. But it's also equal to the other one. I mean, if I switch from overcrossing to undercrossing, it's going to be the same. Okay, so now this is just homotopy. Homotopy just determined by homotopy class of the knot, not the link itself. Okay, so in this case, we can define the product of two skein. Okay, so I defined if I have a link L in the tree manifold and multiply by L prime. So first I isotope so that they are disjoint, and then I take just the disjoint union. Okay, and this doesn't depend on the isotopy, on the how you move, because of this relation here. Because when you move from overcross to undercross, it's still the same, and so this is a well-defined product in this skein model. So this is now, so the skein algebra is become an algebra. So this S at minus 1 of M is actually an. So it's, well, now I changed the ground ring to make it C. Okay? It's a C algebra. It's a C algebra. Commutative C algebra. It's easy to show that the product is commutative. And if the manifold is compact, it's not easy to show that it's finitely generated as an algebra. Okay? So if M is also compact, so M is compact, then this is finitely generated as algebra, but its vector space may be infinite dimensional. Now you know that if you have a finitely generated algebra over C, then it's more or less an affine variety. Okay, so suddenly you need to take care of the nilpotent element. So this means the S minus 1 of N, and if you divide by the neon radical, you will get the ring of regular function on certain algebraic variety. Okay, and it turns out that there is a canonical isomorphism between this algebra and the ring of regular functions on the SL2C character variety. So this is canonical isomorphic to. So this is the SL2C character variety. Of the fundamental group of the tree manifold. Okay, this is a result of, I think this was proved by Bullock and independently by Brzezinski and Shikura. Well, even if you don't divide by the numerical, you get the so-called the universal character variety algebra. Okay, so that is one reason why the skein model on skein algebra is interesting. It can be considered as the quantization of the character variety, and then you can relate the skein algebra to classical objects like the A polynomial and so on. Okay, so this is the first instance where you have an algebra structure on the skein model. Okay. The other one is, the other case is when you have here. So this is the second case when, in the second case, you don't need to specify, Q is still a formal perimeter, okay? But the manifold is restricted. So now sigma here is a surface, so this is just any oriented surface. Okay. And you define the skein algebra. But now I will put a hat here because later I will define something final of sigma to be S of sigma cross 0, 1.
So then if Q is 1, the conclusion is the same, right?
Okay, yeah, sorry. The Q is 1. There's an isomorphism between the S1 and S minus 1. Isomorphism is given by any spin structure, so they are isomorphic, but there's no canonical isomorphism between the two. Okay, so S of 1 is isomorphic as an algebra to S of minus 1, and I think it's this Barrett gave. I mean, every spin structure of the tree manifold would give us an isomorphism between these two. That is the Barrett, right? Okay, so I will define this one as you take the skein algebra of the cylinder of the surface. Okay. In this case, I can define the product from L times L prime. I use just the structure of the cylinder. So first I isotope L, so that it's just in the upper half of this interval, and L prime is in the lower half. So it's just L and L prime. Just stack L above L prime, and then you get a product. Okay? Now, in general, this is the non-commutative algebra. Now you have an algebra, and the content of this statement is that in this case here, well, at Q equal to minus 1, there will be, the ring will be reduced, so the non-radical will be equal to 0. So you don't need to mod out by this one. Okay, and now actually you have non-commutative algebra, and you can take the semi-classical limit, you get a Poisson algebra, and this is exactly the character variety together with the so-called the Venn-Peterson-Goldman bracket. So this is a quantization of the character variety along the Venn-Peterson-Goldman bracket. I think that is the reason of Turayev in 1890, and also later it's made more explicit in the work of Bulov, Froman, and Banya Bartoshinsky. So that's the work of also Bulov, Froman, and Kanya Bartoshinsky. So this is why it's called a quantization. And so as I want to understand the algebraic structure of this skein algebra here. Now if you look at the surfaces, now surfaces can be built from triangle. You have a bunch of triangles, you glue them together, you get the surface. Okay? So sigma here, you can take some disjoint union of so-called ideal triangle, and you divide by some equivalence relation, which, so you have a bunch of triangles like this here, and you maybe identify this A with this A prime, like that. There are many pairs of edges, you glue them together, you get the surface, okay? And so I want to understand the skein algebra through this decomposition. Okay? It turns out that so actually you can look at this as the so-called Sasha Vorel told me this is the so-called modular operand. Okay? You look at the operand of surfaces with well, maybe I'll skip them. So in order to do this, I need to refine the skein algebra, because in this decomposition here, the boundaries here are important. Okay, so I would want to allow a kind of skein algebra with so not only links, but I allow tangles, so that it have the tangles have the boundary points on the boundary of the surface. So let us look at the following. So I define, so this is a sigma tangle is the following object. So sigma here as before, so sigma here is a sigma bar minus a finite number of points where each boundary component must have at least one point. Okay, so this is so again in this picture here, I have here 2 points here and 2 punctures here, for example. Okay, so first of all, this is the one-dimensional compact manifold properly embedded in sigma cross 0, 1. Okay, so I have something like this here. Maybe I go around like this, and maybe I also have some one component like this, for example. Okay. I will, so properly embedded means that the boundary, so I call this one-dimensional manifold, say alpha here. Alpha. So it means that the boundary alpha would be in the boundary of sigma cross 0, 1. The boundary alpha must be there. It's also free. It means that at every point on the link, I have a normal vector field as usual. Okay? But the framing at boundary point, if I have a boundary point here, the framing should be vertical, just along the direction of this interval 0, 1. Okay, the framing at the boundary point, the framing at boundary of alpha is vertical. Okay, so at alpha here, they're just perpendicular to the boundary here and pointing along the direction of 0, 1. Okay, so that is second. And the last one is very important. So, so if you look at it, C is a connected component of these sigma. So for example, in this case here, I have 2 connected components. One is here and another one is here. Okay, so this is C. C is one connected component. You look at, so I call this dc of alpha would be d alpha. So those points of alpha boundary on C cross 0, 1. C cross 0. Okay, so maybe I draw another picture here. So this is C. This is C. And you look at C cross 0, 1. And then there are several points. So these are the, so alpha would come to this point like this here. Alpha comes to this wall, boundary wall, okay? And I want the heights of these points are distinct. So no two would be on the same height. height is measured by this coordinate of this 0, 1. Okay, so distinct heights. So this is, so this in here points in DC FR will have different or distinct height. And this is very important in the consideration.
C is connected component of boundary of sigma minus P.
Right, yeah. So sigma here is already without, okay, so sigma is already sigma bar minus P. So by default, P is not part of sigma, yeah. But you're right, yeah. Okay, so we have different heights here. So, and again, homotopy or isotopy would be in the class of this sigma thing. Okay, so you are allowed to do isotopy, but you have to be in the class, within the class of this here. Okay. And now we define the skein model, and a bit later the skein algebra. Oh, okay. Okay, now we define the skein of sigma to be again the R span of sigma tangle over, so relation 1 and 2 just exactly like what we had before. So 1 here is the skein relation, is Q plus Q inverse of this. So this is 1. And 2 is just this one is equal to minus Q squared minus Q minus 2. But now, because we have boundary points, we need to have something new. And after some search, I found just exactly one solution up to symmetry. Okay, and this is a solution. At first, it looked like a bit. Okay, so let me write the solution. So I have to use. Solution is this one here. So this is the boundary here. Minus and plus should be equal to Q squared plus and minus plus Q to minus 1/2. And this is the reason why I didn't need square root of Q. This one and this one. Okay. So what does this mean here? So this is just part of the surface. Okay. Oh, I forgot. Also, a state of n4 is any map F from the boundary points of n4 into plus or minus. Okay, so maybe I put here a plus and put here a minus. So a state is just an assignment of signs on the boundary points, okay, arbitrarily, plus or minus. Okay, so behind the height here, I also have plus or minus on each point here.
What is the power of Q?
So Q squared, Q to the negative half. Okay? So here, what does this mean here? So this part of the surface, and I have two boundary points here. This shows that this is above this one. Okay? The direction of this boundary component. So this is C, a boundary component, a boundary component, a boundary component here. This point is above this point. The direction here just shows us the height, the order of the height. The height, okay, of these two components. And if you have a minus above a plus, you can somehow switch by this rule here. Okay?
So the tangles are with states.
This is state tangle. Yeah. State is tangle. Okay, so we have here this condition, and if you do this, then you can reorder the height so that the positive are always above the negative. Okay? So with this here, any component C here, you can reorder the points so that you will have here plus, 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 and then minus, minus, like this. You can always do this using this relation here. Okay? But I need more relations, so these are just the trivial one. So this is, if I have here plus and plus, then it should be 0, the same as minus and minus. Okay? And then the very last one is that if I have here a plus and minus, and that would be q to the 1/2. Sorry, minus 1/2. And that's all the relations that I need. Okay? So as I said, at first it looked like, well, where do I get these from? Well, that's the only solution up to some symmetry if you want to make the theory work. Okay? You want to make the theory work. So what is good with this? I mean, why do I need all this? I introduced all this just to have the following decomposition. Well, suddenly all this plus minus here. I mean, why do I have states plus minus here? It's because this is SL2. You will have two fundamental states in SL2. Okay? And, okay, so, now it's not difficult to, now if you look at this here and you look at diagram, tangle diagram on the surface, using this here, you can avoid any double point, any crossing, okay? Using this one here, you can remove all the trivial component, and this one here, you can remove all the trivial component. So, a basis, so this is an R basis of this S of sigma is given by sigma tangle diagrams. Okay, there's no crossing, no trivial components. I mean, if you have trivial component, it becomes this number, or if you have trivial component like this, it becomes some number here. Okay, and dc of n phi would be like this here. I mean, it's like this picture, like this picture. So it means that order, height order, the height order on each dc of n phi is increasing along the direction, the positive direction of the C. Okay. So that would be, they are very easy to prove this using standard argument of the diamond lemma. That you have as an algebra, as an R model. Okay? And now you can define product. Product you define as usual n phi times n phi prime. Again, because you use the cylinder structure, you put n phi above n phi prime, then you get the product as usual. Okay? So now you have an algebra over the ground R. And it turns out that with this definition, you can have a nice decomposition in the spirit of opera theory. So, what I want to understand is how can I relate this skein algebra to the skein algebra of the triangle. Well, the original skein algebra, when you don't have anything on the boundary, embed into this bigger algebra here. Okay, as usual, this bigger algebra is very nice, and it behaves well under gluing. So if I have here, two edges, so two boundary edges. So A and B. So if I have a 1, this is A, maybe I draw a straight line like this here, and this is B in sigma. Well, sigma may be disconnected, so maybe two disjoint parts, or maybe AB in one connected component of sigma. It doesn't matter, okay? You can glue these two to get a new surface. So this is C. Okay, you glue this to A and B, and there's only one way to glue this up to decomposition so that the orientation is compatible. So only one way to do this, okay? So this is sigma, and you get this is sigma prime just by gluing. So this sigma prime here is equal to sigma, and you identify A with B. So A should be equal to B. Okay? You get another surface of the same finite type, or the so-called border surface with punctures. Okay? And now we want to understand what is the relation between S of sigma prime and S of sigma. Okay, what is the relation? Because if we can do this, we can further decompose. So we glue these two from sigma, you get sigma prime, and if we split sigma prime along C, you get back this sigma. Okay, so if you have an ideal triangulation of sigma, you just split along all the edges to get a bunch of ideal of triangles, and then you somehow recover this algebra here. Okay, so we look at the following. It's very natural to let me just use this picture here. So maybe I use so I will formulate the precise. Yeah. So if this is some delta is here, some alpha in the glue in sigma prime here. Okay. Well, maybe at some boundary. So this is another boundary part, and then on this boundary part, I already have plus minus for example. Okay. Now I leave this here. I just formally split this, then I get this picture. Here I also have plus, minus, okay? Except for the boundary points of this splitting part here. I mean, here they are not in the structure. I mean, I can isotope a little bit so that this alpha is transversal to this C. When I cut this along C, I get this picture, okay? Well, certainly I have to care about isotopy, but that will be later. And actually all these relations are introduced so that it's behavior under isotopy. But I have to look at this. I mean, if I split this, say if there are K points here, there will be K points here, okay? Now I need first to order them, the height order, and secondly, I also need to put there the state, okay? So first, I will fix any height order on this alpha interface with C. Okay. So there are 3 points here. I fix arbitrary order, but I fix that. Say for example, maybe this highest. This is say 1, 2, and 3 here. But it doesn't matter. Just fix any order.
The same.
Yeah, the same here and the same here. So actually I fix order here, and when I lift this, it's the same here. So order on this one, and then we lift it, we have an induced order on each of this. Okay? So we fix any order. And now we have to take care of the state. States can be plus or minus. So I put here some epsilon 1, then this should be also epsilon 1. If I put here epsilon 2, this would be epsilon 2. This is epsilon k, this should be also epsilon k. Okay? So epsilon here, so epsilon 1 up to epsilon k here, they are in just plus or minus. Okay, so the only rule is that if this is epsilon 1, this must be also epsilon 1. So they must be of the same state when you glue the thing together. Okay? So there would be 2 to the k. 2 to the k possible states. When I do the split. Okay? So now I can form the following elements. So I can form the following elements. So I can form that phi of alpha to be the sum of these 2 to the k states of this alpha theta with epsilon. So between the epsilon is in plus and minus to the k. Okay, so this epsilon is epsilon 1 up to the epsilon k. There are 2 to the k such state, and I just assign that state to, this is the lift here, this is alpha theta. This is alpha, this lift here is alpha theta, and I fix an arbitrary height order and just sum over all possible states like that. Okay, so the theorem is that the map is well-defined. It doesn't depend on the height order here. It gives us an embedding of the first of this one into this one. Okay, so phi here from this skein algebra, this skein algebra sigma prime to as a sigma is well-defined and it's an embedding. Okay, so you can, and also we have this simple associativity. So, well, it means that if I glue or I split, if I split by using 2 different ways, I get the same result. So this is the map from, so let me draw the diagram here. If I begin with sigma over A equal to B, and then C is equal to D, okay? So I can map, this is the map phi here, sigma over A equal to B. You map here sigma over C equal to D, and here you map to sigma, oh, this should be S of this. Okay. So S of this, and then S of this, then S of this one, and this is just S of sigma. Okay. Then the diagram is commutative. It's almost obvious from the definition. The only thing is that you need to show that this is well-defined under isotopy of the diagram. Okay, and then the associativity is just obvious. So this is kind of modular operand on surface. Okay, and then the skein algebra is just a co-algebra of this modular operand. Okay, so if you use this here, okay, I think I will finish in a minute. Okay, so if gamma here is the triangulation, and F here is the set of all faces, then you have a map from skein of sigma embed into tensor products of the skein algebra of each triangle. Okay? And this S of triangle here, it's just we have a triangle here, and the basis is very simple according to the thing that we had there. It's just object like this. So this entry has a very simple presentation. A very simple presentation. Well, it has 12 generators with explicit, so with 12 generators. And these are all, it belongs to the class of, it's called quadratic algebra. So actually all the relations of the form x, y, q should be equal to something of degree less than or equal to 1. Okay, so the q commutative would be equal to something of degree less than or equal to 1. Most of the time it could be 0, but there's 1 or 2. And so you can, and any representation of this triangular algebra, of this symbol here. I mean, if you have a map from here to any algebra A, then you can, so this is any row, you can just have row to this symbol of this A here. Okay? And one of this, and I can give an explicit map from this one to the so-called the Chekhov algebra of the triangle, and then we recover the quantum trace map of Bonahong and Wolf. So I think I've run out of time. Thank you very much for your attention.